In this work, we present how many tokens do 3D point cloud transformer architectures really need. This is the first study to systematically investigate token redundancy in dense point cloud transformers. Efficient 3D point cloud processing is essential for applications such as autonomous driving, robotics which demand real-time analysis of millions of points in both indoor and outdoor environments under strict computational constraints. State-of-the-art models such as PTV3 and Sonata leverage transformers to process dense 3D point clouds and achieve superior performance across indoor and outdoor tasks. However, their main limitation remains the quadratic O(n)² cost of self-attention in both computation and memory. We find that these 3D transformers are highly redundant in their token usage. Even when compressing up to 90% of tokens during self-attention, the PCA visualization shows that the features remain consistent with the original. We propose GitMerge 3D, a globally informed graph token merging method that adaptively merges redundant regions, either aggressively or moderately, starting with the latent feature of the 3D point cloud tokens before the self-attention calculation. We define an energy score for each spatial area. Higher scores indicate more informative area, while lower scores correspond to less informative, more redundant tokens. Based on the energy scores, each region is merged either moderately or aggressively, with aggressive merging compressing over 95% of tokens. The merged tokens continue through self-attention and are later unmerged using a simple duplication mechanism. With an 80% moderate merge and a 97% aggressive merge, both Sonata and PTV3 maintain almost the same performance, while achieving 4 to 6 times savings in memory and computation. Even at 95% token merging, fine-tuning for only 10% of the epochs preserves full performance for PTV3 and Sonata. We illustrate that GitMerge 3D outperforms other token merging methods on 3 different indoor datasets: ScanNet, S3DIS, and ScanNet 200. We further demonstrate the effectiveness of our method and the high redundancy of 3D tokens in transformers across outdoor segmentation, object detection, and 3D reconstruction. The table shows quantitative results on the new scenes dataset, while the image illustrates qualitative results for reconstruction. Here we show the energy score visualization in the middle, and on the right, the difference between predictions with and without 90% token merging. Here's another example showing minimal changes, even with 90% moderate merging applied. We can clearly see that areas of high energy are concentrated on foreground objects, which should not be merged carelessly, while background regions have lower energy, containing more redundant information, and can therefore be merged more aggressively. We also demonstrate that GitMerge 3D can be applied directly to downstream task training with the self-pretrained Sonata model, highlighting the potential of token merging to train large models efficiently without sacrificing accuracy. More surprisingly, our attempts to replace the self-attention layers in PTV3 with parameter-free alternatives, for example pooling and shuffling, showed competitive performance compared to the base model 66M EOU vs. 67M EOU. This suggests a potential direction toward more efficient architectures for dense point cloud processing. Thank you for listening. For more details, please visit our webpage using the QR code below.